Good morning, all. My name is Corey Moran. I am more or less the creator of this activity for this nature camp session. My wife and myself actually created this, but I'll be the one who's got conned into recording this for you guys. Okay, so today's lesson is going to be on cell velocity, or the movement of cells, and how they go about doing that, and why it's important for us as individuals. Now keep in mind, I'll be going over the presentation with you right now. This lesson is pretty short, so you shouldn't have to spend too much time working on this as it is. And then I'll kind of bring up your printout of what you are looking at, and I'll kind of try and go over all of that with you as well. And then I'll point out some links that you're probably going to have to go to ensure that you are building your cars and what else have you to the correct steps there. But again, that shouldn't be too big of an issue because Mafani should have uploaded all of this, hopefully, to the Google Classroom, so you could just click on those links. If not, for whatever reason, we can't, you're probably just gonna have to click or type in the URL into your browser and get that information that way. Because I'm not sure I want to show you the videos here. I'm not sure if I feel like it would take more time than probably quicker for you to do it on your own. But without further ado, let's get started, shall we? Click. All right, just some background information as to what we're talking about here. Some of the research that's going on right now through some biological departments throughout the world. There are a number of studies that look at the velocities or movement of cells as reasons why we care about how fast they do these things and why they move the way they do. For example, the study of the velocity movement of red blood cells is something that we care about into tumors, which is beneficial to study of how to treat such things as cancer, because obviously, as we know, cancer can spread throughout the body, and they travel through our veins, they travel through different systems within our bodies, and we care about how fast they do that and how fast they move throughout therein. Okay, so that's one reason why we care about the velocity or movement of some of our blood cells. Some other reasons we care about movement of cells is, for example, like I just said before, the spread of cancer by metastasis, or the growth of new cells. Metastasis is, again, that growth is a new growth or tumor, is driven by a set of mutant proteins called oncogenes. Excuse me, I'm a little thirsty, which causes cancer cells to multiply uncontrollably and promotes their ability to move. And again, the reason why we care about this is because these cells tend to have their own mode of transportation, whereas some of your cells, such as blood cells, like I just went over, move as fast as the fluid in your body allows them to. Whereas these guys have their own means of transportation, their own means of movement. So think about it in relation to us. We have our means of transportation is obviously our legs, or when we're younger, our ability to crawl. These guys have their own means of movement, whereas some of our other cells do not. Okay. And then keep in mind that it's not all doom and gloom for us. I'm going to move this just over down here real quick. Might have to move that back, but we'll see. White blood cells have a means of movement all their own, kind of like cancer cells do as well. For example, new research suggests that white blood cells have their own special way of swimming throughout our bodies-ish. So I use the term swimming loosely, but I guess you could probably think about it that way. Which biologists have dubbed molecular paddling. So as you can see, this used to be a video, but I ripped it. Basically, you can see that this is undulating a little bit or looking wavy. This is a white blood cell, and it creates these almost like it almost does like a breaststroke pattern, you know what I mean? And it creates these proteins that basically act as paddles for itself to basically move it or boost it along in the body. Okay. Now, what does this have to do with what we're doing today? Well, and there's some talk about cell migration in fibroblasts and demonstrating rapid, slow movement here. And again, we're talking about this sort of protein movement here where it kind of moves out and kind of moves back and forth, that sort of thing. But for the means of our activities and what we're looking at today, we're going to be looking at more of motion, how we calculate it, how do we figure it out, and that sort of thing. So for observing motion, how is a frame of reference used to describe motion? So again, this will be something we kind of discuss, but again, since this is more of a recording, it's something you're just going to have to think about on your own. So again, frame of reference is, think about it this way. You're on the ground, you're looking up, and you can see somebody jumping from a plane. So in your frame of reference on the ground, the individual looks like he's moving towards you, right? Now, let's change our frame of reference to the airplane. Let's say that we are jumping from the plane with this individual. The individual looks like he's not moving at all. He's right there with us, right? So it's ideally, it's good to keep in mind frame of reference when it comes to motion, okay? And what is motion? Motion is an object's change in position relative to a frame of reference. So that's why I just kind of talked about frame of reference for you. I'm gonna move this again. Hopefully this is the last time. Frame of reference is a system of specifying the precise location of an object or time and space. Okay? When an object or a cell changes position, with respect to a frame of reference, the object is in motion, okay? So again, that's all about frame of reference, that sort of thing, okay? Observing motion continued. Distance measures the path taken, whereas displacement is the change of an object's position. So again, we're talking about this idea, what's the difference between distance and displacement? The best way that I can explain it is right here. The change in position of an object always includes a direction, is displacement. So as you can see in this little graphic right here, this individual started here. The yellow is the distance traveled, whereas as you can see here, displacement is just how far from where he started to where he ended is displacement. Okay, so in the diagram, yellow equals distance. The black arrow here is displacement, okay? Pretty straightforward. Again, keep in mind that displacement, say this guy ran around here in a complete circle and ended where he stopped, his displacement would be 0 because he ended where he started, okay? But in terms of distance, distance doesn't care about how far they ended from where they started. They care about total, okay? Which is the yellow arrow here. Okay, so that's the difference between the two, more or less. Speed and velocity. What's the difference between speed and velocity? And again, I set this up for a group discussion sort of thing, so we can kind of discuss it one another, see what kind of ideas we have. But again, as this is a recording, we don't really have that luxury. But again, just kind of think about it to yourself and come up with an idea. Okay. Excuse me. What is the difference between speed and velocity? Speed tells us how fast an object moves. Okay, whether it be miles per hour, kilometers per hour. In the physics world, we use meters per second, and that's what we're going to be using pretty much throughout this entire activity, and what else have you. And velocity tells us both speed and direction that an object moves. Okay, so in the physics world, velocity is something that we care about a lot, and it's something that we are going to be using today. Okay, so we're going to be using speed. We're going to be using velocity because it gives you a speed and a direction as to where something's moving, because obviously it helps to know how fast something's moving as well as a direction as to where it's going. Okay, so again, I got our definitions down here as well, which I already pretty much gave you. Excuse me. Velocity is described relative to a reference point. And again, I went over reference points a little bit with you already. Direction is described as a position or negative along a line of motion. So again, by convention, up, right are usually positive, whereas down or left are negative numbers. We're not going to be messing around with that a whole lot, or if any, today at all. I'm just trying to give you guys an idea later on if you decide to take a physics class. These numbers end up becoming negative for almost no reason other than common sense for the most part. But again, decide to take physics, we'll deal with that a little bit later. And then we start talking about this idea of resultant velocities, but again, not so much something we're going to be talking about today or using today. Calculating velocity is something you're going to be doing today, so we're going to talk about this a little bit. I got an example in here for you, and then we'll kind of go back to, again, our lesson plan a little bit. What do you need to know to find speed of an object? To calculate speed of an object or the velocity of an object, you need to know two different quantities: distance it traveled and the time it took that object to move that distance. Okay, now when we're measuring these, our distance need to be in meters. Okay, and our time needs to be in seconds. Okay, so hopefully you guys have meter sticks. If you don't, you're going to need to be converting some stuff. You're going to be needed to convert centimeters into meters, because I can only imagine that if they gave you a ruler, you're going to have to use the centimeter side. Okay, so you would measure out however many centimeters you have and divide it by 100, and that'll give you meters. Pretty straightforward. Okay, hopefully you got that much. Seconds, we all have cell phones. They all have stopwatches. Okay, should be pretty straightforward. Okay. Calculating velocities. Average speed is calculated as distance divided by time. So by social convention, velocity equals distance divided by time. SI units is basically SI unit is standard individual units. They're antiquated, meaning, like, for example, us in the US, we use miles per hour. Miles is based on the foot, whereas the rest of the world uses kilometers per hour, whereas we use, like I said, miles per hour. Kilometers per hour is based on the meter, whereas, again, a meter is a base 10 unit, whereas the rest of the world uses that, whereas you and me live here in the US, we use miles per hour because we like non-antiquated units. Same thing with Fahrenheit and Celsius. Celsius is based on the temperature which water boils and water freezes. Whereas us, we use some arbitrary number, basically 32 degrees is where water freezes for us. Whereas in Celsius, it freezes at 0, which honestly makes more sense, but I'm not here to go off on a tangent. Okay. Constant speed equals distance in equal amounts of time, whereas instantaneous speed is the speed at a given time. So again, if we were graphing this, which I do in my own class, we could kind of pick out these sort of things. But again, that's not something we're going to be worrying about or talking about today a whole lot. Okay, but again, this is our formula we're going to be using. Distance or velocity, again, equals your distance in meters divided by time in seconds. Or if you want to see it like this, V equals distance divided by time. Okay, so again, I set it up as a fraction, but if you want to see the division symbol, that bar is just a division symbol, more or less. Hopefully you're a little bit keen on fractions. Okay, so let's look at an example here on how to calculate these sorts of things. So this is what we're looking at here. A metal stakes are sometimes placed in glaciers to help measure a glacier's movement. For example, in 1936, Alaska's Black Rapids Glacier surged at swiftly as 89 meters every 86,400 seconds, or 1 day. I converted this into 1 day for you in seconds. I had this placed as 1 day for my class, and they had to figure it out in seconds and convert. But again, we're not worried about conversion today. So just being able to calculate these sorts of things is good enough. Down the valley, find the glacier's velocity in meters per second. Remember to include a direction. Okay. So again, the first thing you need to do is just pick out what we have. We have 89 meters. Oops. Let's go back. So again, given T equals, what's our time here is 86,400 seconds. So I would write that down. Our distance here is 89 meters. So again, I would write that down. And again, the direction is down the valley. Unknown velocity in meters per second. What is it? We don't know. We have to figure it out. So again, first thing we do is perform any necessary conversions. I did that for you. In your own activities, depending on if you're using centimeters, you might have to convert centimeters into meters. And again, that's just measuring your total centimeters. Dividing that total by 100 will give you meters. Okay, simple as that. And again, you write your equation for speed. So again, here's the equation for velocity again. So we're going to take our distance, put it on top, and divide it by our time. So again, this is what it should look like. V equals distance divided by time. And then we're going to have 89 meters on top because that's how far it moved in a day. And a day is 86,400 seconds. So our overall velocity is down here, 0.001 meters per second. So as you can see, this thing didn't move very much every second, more or less, okay? But yeah, so this is very much a example of how you're going to be doing this, okay? And that is our presentation. Let's take a look at our actual lesson plan, shall we? And kind of discuss what you're going to be doing. Okay, so this is what everybody should have in front of them as a handout. Just project description, and again, you can kind of read over this yourself. Project objectives, you can read over this yourself as well. Cultural connection, normally we would have somebody talking about velocity or movement a little bit in class, but I'm not sure if that's the case this time around, so I kind of just included some stuff in here. For example, Native Americans have running in their blood or movement in their blood, more or less, because again, we didn't always have the horse, quote unquote, that was brought over. So again, we needed ways of communicating without, well, with means of travel, obviously, which means, but before that, the fastest means of transportation, depending on tribe, was running. Okay, so historically, wow, look at that. Historically, whatever. Historically, Native Americans ran as messengers. In the 1860s, a fox runner, or from the Fox tribe, in his mid-50s, ran 400 miles from Wisconsin to the Missouri River to warn stock Indians of an impending attack. Okay, which is really impressive for the 50s, or for a Native American in his 50s. I mean, that's just amazing. Okay, I don't have to go through all, I'm not going to go through all this, but it's there for you to see that as Native Americans, we were always really good at running, moving through, the prairie and what else have you. Okay, but yeah, okay, here's some of the standards we're going to be addressing today. Again, this would have been our schedule, but again, as most of this is, it's kind of dependent upon you as an individual to work through this. Obviously, you can be done within like an hour, hour and a half, depending on how fast you decide to move through this and how well you get through it. Okay, so some of the stuff, our first activity here is you are going to be looking at these vocabulary terms and basically just writing down your definitions for them. And again, I don't know how you want to do this. If you want to take pictures of them and upload them to your individual teacher, or how else you want to do it. I think that's how I'm doing it with my group. I don't know how you're doing it. If you're uploading it to Google Classroom, I don't know. If you're emailing it out to Mafani, I don't know. Okay, and then kind of discuss these questions and kind of look over them and come up with answers for them. And again, all this I pretty much went over in the PowerPoint as well. Okay. Again, same with these questions. Next, we're going to be doing walk, jog, run, hop. Okay, what are we going to be doing? Well, you're going to be measuring out about 8 to 10 meters. So again, you probably do this outside somewhere. Okay, and again, you'll have to figure that out based on your depending on if you have a meter stick or not. You'll have to do the calculation there to figure that out. Time yourself walking this distance and record it in the table below. I'll show you the table. Do this 3 times and record your results in the table. Calculate your averages. And again, to figure out averages, you add up your times, divide by how many times you did it, which was 3 this time around. Okay, and I got it right there for you. Calculate velocity for each trial. And then again, you're going to go through this again for walk, jog, run, hop. So again, your tables are here. So walking distance will all be the same depending on what your distance is. If you did 8 meters, great. If you did 10, so if you did 8, you'll put 8 down here. If you did 10, you'll put 10 down here, and your average will probably be the same. Your time will be different depending on what you're doing. Obviously, you'll have a stopwatch for that, and then you'll just kind of stopwatch yourself every time, and then you'll calculate out velocity using distance divided by time, and then you'll write them in here. And then you'll do the same thing for jogging. running, and then hopping. Okay. And again, same thing. Once you're done with that, you'll take pictures of it all. Well, you'll do the end of questions here for you that kind of wrap things up. Take pictures of all that, upload it, that sort of thing, or email it out, however you want to do it. And then this one, you're going to be making two different types of cars. One's a coffee cup car and one is a balloon car. And you're going to basically be comparing and contrasting which one is the better design choice for movement or velocity. I got what you need right here, but you should have that in your kit. Here is the YouTube page, or excuse me, YouTube video for step-by-step how to see somebody build it. I would recommend using it. I have the directions down here as well. Keep in mind that there's one caveat I want to add if you're going to be using this video, which I recommend you do. You're going to see this guy take the cap or the lid of the coffee cup, and he's going to put a paper clip on the end of this string of rubber bands. He's going to pull it through. That paper clip, I want you to tape it to the lid. Otherwise, you run the risk of it spinning. Okay, that's the only thing I want to add, because when I do it in my own class, I usually hot glue it down, but tape should work fine too. And then you're going to be constructing a balloon car as well. I highly recommend procedure-wise. I didn't even bother. Well, I did create some procedure for this, but I would recommend watching this guy do it. He does a really good job of explaining how to create this thing, and I recommend you do so. Oh no. Oh, wow. Uh-oh. Okay. All right. And again, you'll be comparing and contrasting these two. Here's what you need to do. You'll basically wind up your coffee cup car. You'll set it loose. Once it goes a certain distance, you'll be timing it. Once it stops, you'll write the time down here in seconds. Then you'll measure from where it started to where it stopped in meters. Write that down here and do velocity, figure out your averages. And then you'll do the same thing for your balloon car. Then you'll just wrap up by answering these questions, and basically you're done. Okay. If you have any questions or need some sort of clarification, by all means, ask somebody. You'll be able to help you out with that. Okay. All right. Awesome. I think that's everything. Awesome. We're going to stop sharing here, and then we're going to stop recording.